Section 3.1, this is video number 3. We're going to talk about piecewise defined functions and greatest integer functions. A piecewise defined function is a function whose rule includes several formulas. The formula for each piece of the function is applied to certain values of the domain as specified in the definition of the function. Example, for the piecewise defined function, find each of the following. Now, again, a piecewise defined function, we're given a rule for the function who has several formulas. For this one, notice that we have f of x equals. So this is the top one, x squared plus 2x, if x is less than 2. So we're saying that for x values less than 2, we're going to only use the top equation. And for 3x minus 5, we're going to use only if we have x values in between 2 and 20, including 2 and 20. Now, for this, if I look at 0, so f of 0, if I were to plug that into here, I know that I would look to see which domain restriction does it fit into. Well, 0 is not in between 2 and 20, so we're not going to use the bottom equation. We're going to go ahead and use the top equation. So that means I'm going to do 0 squared plus 2 times 0. So when I plug that in, I get 0. So f of 0 for this piecewise defined function is 0. When I plug in 3.6, 3.6 is larger than 2, and it's in between 2 and 20, so I'm going to use the bottom equation. So 3 times 3.6 minus 5. Now I just have to go ahead and simplify this. This is equal to 5.8. For the next one, if I do 24, and if you look, 24 doesn't fit in the top equation because it's not less than 2. It also does not fit into the bottom equation because it is not in between 2 and 20. Therefore, f of 24 is not on a graph if we were to graph this out. So this would be not defined or no solution. And lastly, the domain. So if I think about doing just an x value number line here without actually putting this on graph, I have 2 and I have 20. So at 2, I have an open circle and I'm going this way. But then for this 2, it's a closed circle, and I have numbers going all the way up to 20, including 20. So the domain of this function is actually negative infinity to 20 bracket, including that. Now, I'm going to actually show you how to do this in your graphing calculator. We will be graphing these by hand in the next section, but just to kind of get ahead of ourselves, we can go ahead and do this. So if I go to my graphing calculator and I plug in x squared plus 2x, we know that's a parabola. Oops, y equals, so x squared plus 2x. I know this is a parabola. However, it said we're restricting our domain values to values less than 2. So in order to write this in your calculator, you can hit the division symbol, and then you always have to do parentheses. So x values less than 2 would be, you go to x. To get the symbol, you go to second math, because notice it says test right there, and we're doing values less than, which is number 5, and close parentheses. And actually, I forgot to put in the 2 there, so 2, close parentheses. Now, if I were to graph this, notice on my graph, it doesn't graph the whole parabola. It stopped right here. So we only have values that are less than 2. So notice that our graph is only this piece right here. Whereas if I didn't put this piece in, I would have graphed the entire parabola. But again, because the function rule said we only want x values less than 2, we do not do that. So let's go ahead and do the next one. Now the next one's a little bit harder because your graphing calculator for some reason is a little finicky and it doesn't like you to write in equations like this. So instead of writing it like that, you have to write it in 2 separate ways. You would have to write 2 is less than or equal to x, and then x is less than or equal to 20. And then you would want to put this whole thing in parentheses in your calculator. So for some reason, anytime you have an x value in between 2 numbers, you would have to write it as 2 separate ones, and I'm not exactly sure why. Now, so let's go to this second one. We have 3x minus 5 is the equation. So then use the division symbols to show now we're going to do the rule. So I want 2 parentheses. We had x, and then go to second math. We want less than or equal to, which is number 6. Less than or equal to 2, close parentheses, and then another set of parentheses. Now we have x. Second math is less than or equal to, so number 6, 20. and then close both sets of those parentheses. Now if I hit graph, I'm going to do the second equation. Oops. So I must have put something in wrong. So x is not less than or equal to 2 at that first one. I didn't realize I did that. So it's greater than or equal to. X is greater than or equal to 2. So I'm just going to switch it by doing this. Put the 2 there and the x. Sorry, I didn't realize I did that. So now if I go to graph and look at this, I know that my graph is going to have the first part, and here's the second rule function that I have, and the rule says we're starting at 2, and we want numbers that go up to 24. So I'm going to change my window, and actually I'm going to do a y x maximum of, let's do 25, and then let's do a y maximum of 25 as well. So here's my graph. I notice that, oops, well, it's still going to go up. So 25. Let's go up to, let's do 75. Because that's going to show us where it's stopping. Now, I don't usually need to do my whole window like this, but then you can see your graph stops here at 24, and that's again how we got our domain. So again, eventually we will be graphing these by hand, but this is how you would do it in the calculator. So make sure you know how to do that because we will practice that as well. But you know, as you've seen, doing that takes a while, and so sometimes doing that is a lot longer than actually just looking at what you have on paper. So if you look at the next example, we have 3x squared minus 5 if x is greater than or equal to 4, and 2x plus 15 if x is less than 3. So if I look at this, I want to evaluate this function for 0. 0 is less than 3, so it goes in the bottom one. So 2 times 0 plus 15. So 2 times 0 is 0, so this gives me 15. If I do 3.5, 3.5 is bigger than 3, so I can't use the bottom equation, but in this case, if you look at the next one, it's not small, it's not larger than 4, so because of that, this is not on our graph, so this would be no solution. And then if we do h of 4 and plug it in, well, 4 is greater than or equal to 4, so we're going to use the top equation, so 3 times 4 squared minus 5, which would give me 16 times 3 minus 5 is 43. And the last one, the domain. So for this one, if I were to graph this, I would have x values less than 3. So here is 3, and it's not including 3, so it would go this way. And then at 4, we're including 4, and I have numbers bigger than that, so that goes this way. So my domain's going to be parenthesis negative infinity to 3, parenthesis union bracket 4 to infinity. And of course, if you were to graph this on your graphing calculator, you would see that as well. Now let's go ahead and talk about the greatest integer function. The greatest integer function is a piecewise defined function with infinitely many pieces. The greatest integer function for any number x, you're always going to round down to the nearest integer less than or equal to x. And this is what the function looks like. Sometimes in some books you will see it written with 2 lines like this. If you ever see that, that also means the greatest integer function, so sometimes you'll see that in a book. Our book uses this right here. For the greatest integer function, the domain is all real numbers, so you can plug anything in for x. However, your range or your output is going to just be integers because you're rounding down to the nearest integer. If we were to write a rule for the function, the rule for the function would look like this over here. So if I want to think about graphing the greatest integer function, if I, let's say, start at 0, well, 0 rounds down to 0 because it's not, it's already an integer, and I can be equal to 0, so I have a closed circle here at 0. If I have 1, so if I do f of, let's say, 0.1, so 0.1 then rounds down to the nearest integer, so that would round down to 0 when I plug it into the greatest integer function. If I did f of 0.2 in the greatest integer function, so this is f of x is equal to this, that's what we're using. So 0.2 rounds down to 0. If I do f of 0.3, that also rounds down to 0. If I do f of 0.4, that rounds down to 0. etc. So if I do f of 0.9, it rounds down to 0. If I do f of 0.9999, etc., that also rounds down to 0. So basically, everything rounds down to 0, and except for when we get to 1. So we're going to put an open circle here, and I have all these at a y value of 0. So for any x value in between 0 and 1, it rounds down to a y value of 0. So then the next one that we would do is in between 1 and 2. So if I did f of 1, that's just 1 because it's already an integer. So if I do f of 1.1, that rounds down to 1. So that would be somewhere in here. If I did f of 1.5, that rounds down to 1. So again, it's a y value of 1, so it would look like that. If I did f of 1.9999, it rounds down to 1, except for when we get to f of 2, that's equal to 2. So this would be an open circle here, and it goes like that. So then if we continue this pattern, this is what, and it would keep on going, the greatest integer function would look like. Some of you might recognize this. Some of you might recognize it. You might have called it before a step function because it looks like steps. However, we're going to call it by its real name, which is the greatest integer function. So again, for this function, you're always rounding down to the nearest integer. So that's what the graph looks like. And yes, you do need to know what the graph looks like. So let's do these examples. So I would maybe stop and pause it and see if you can do them on your own first, and then go ahead and unpause it, and we'll do them together. All right, for the first one, we have negative 5.1. So negative 5.1, we're rounding down, remember, to the nearest integer. So if you put negative 5, you would be wrong. This rounds down to negative 6, because again, if you think about a number line, if on my number line I have negative 5, and this is negative 4, and this is negative 6. Negative 5.1 is right here in between negative 6 and 5, so that rounds down to negative 6. F of 3.2 rounds down to 3. F of 5/4 rounds down to 1. F of 0 would just be 0. F of pi is 3.14, so that rounds down to 3. Now, for this, we do have the greatest integer function on our calculator. So if I go back to my home screen and I go to math and I go to number, look at, you have int right here, number 5. So if I hit number 5, and just to show you, if I did negative 5.1, notice that it rounds down to negative 6. So I can do it again. So math, number 5 is an integer. So if I do negative, let's say 5.5, notice that would round down still to negative 6. And I could keep on doing that. If I go to my y equals and graph this, the graph on your calculator is not going to look quite as good as the graph that we did because we have those open and closed circles. Which your graph, if you graph it, you can't tell. So actually I'm going to hit zoom 5. Not zoom 5, sorry, zoom 6. And notice here you can see our stepped function. So it looks like those steps. And if you were to go to the table, notice you would get the numbers for all the integers. So if I change my window to, let's say, let's go by, instead of 1, because those are the integers, let's go by 0.1. And then go to my table. Notice that all these numbers are rounding down to negative 4, and it happens for everything. So if I go, I'm going to change my window and start at 0. So if I go to 0, notice that everything between 0 and 1, not including 1, rounds down to 0. And then as soon as you get to 1, the same thing happens, etc. So again, make sure you know what this looks like, and we will go ahead and talk more about piecewise defined functions and the greatest integer function in class.